Good morning, all, and welcome back to the class on smart materials and structures. Yesterday, I could not take the class due to some other assigned job, but it's good that you people have submitted the assignments which was given to you all. Only Harsha has not submitted the assignment which was being assigned yesterday,
Ma'am, submitted, ma'am.
where I am not able to see in my mail.
Ma'am, I'm submitting, ma'am, yesterday. 9:36 around 9:35.
To which email ID you have sent me? Mohan Ambal has sent Sandesh. So,
Uh, ma'am, again I am sending, ma'am. No, just,
no, wait. Yeah, Ravori Sri Harsha, right?
yes, ma'am. Yes, ma'am.
Yeah, it's there. All I've submitted. Okay, fine. So your assignment is completed and all of you have submitted. So I've given the attendance for yesterday's class, right? So we'll start up with today's class actually. So can you remember what we were dealing in the last class? Can anyone just give me a glimpse of it quickly? Who will be telling me out? Sandesh?
Scaling of electrostatic force.
Yes, scaling of electrostatic forces. So we have completed all the factors which were involved in doing and scaling of an actual electromechanical system into an micro level. So it's very essential to do scaling in various factors what we have dealt in last previous two sessions, right? So this mainly included, if you remember, like we have dealt with each and every parameters, right from scaling in geometry to rigid body dynamics, electrostatic forces, electromagnetic forces, scaling of electricity, scaling in fluid mechanics, as well as heat transfer. So if they ask you to just figure out the significance of scaling of mechanical system, you will just explain these informations. And if they ask you to explain step by step features, how to do a miniaturization of an electromechanical device, so then you need to explain all these factors in depth, what we have taken to explain like around two sessions. Fine. So next concept what we have in our syllabus is related to fundamental theory of MEMS, what you have to understand. So now you know what you mean by MEMS, its applications, disadvantages in comparison to IC chips, and various phenomena we studied, including the scaling factors. And we also dealt about the miniaturization. So now you should understand how these MEMS devices are developed. So this basically comes into the fundamental theory. If in syllabus they were supposed to specify as fundamental theory of circuit system, so then you need to show the circuit system and mathematical equations, all those steps. But in syllabus, it is only mentioned as fundamental theory of MEMS, and hence we are focusing on how these MEMS devices are developed or fabricated, right? So for every MEMS device to be made, development of a thin film is very much essential. This is even also called as a mask or deposition of a thin film on the material. So this deposition, what we do very carefully, will be within the very minor range of few nanometer to 100 micrometers. It cannot even be an 1 mm thickness as well. I have told you clubbing of all the micro components together can have a thickness of 1 mm. But MEMS device consists of many micro components as we have discussed, like micro actuators, micro sensors, microstructures, microelectronics. So all these will be within a deposition layer of few nanometers to 100 micrometers. Combination of all these will yield for 1 mm thickness, right? So first and foremost thing what you have to understand is about the deposition. How do you deposit the thin film of the material on the given substrate? So what do you mean by a substrate? You should be having something to hold on, right? So you'll be having a surface on which you can apply a thin film of the material. So the basic surface what we'll be using will be called to be as a substrate. And this substrate could also be made up of different materials, right? So the most common substrates which are used could be on silicon, glass, or quartz. Quartz is a common type of piezo material which is available in nature. And glass. So this is very inexpensive and cheaply available substrate, right? The glass. Usually when you want to go on with a good amount of addition to the thin film, you need to opt and better substrate. So for that, silicon is the most feasible one. But if the materials are of ceramics and when you subject it for some to and fro motion like in cantilever and all, you should be having a good addition. In that case, we can even use an stainless steel of certain hardness material to be as our substrate. So that differs from application to application, which is the substrate which has been essential. But for deposition, you should be having some surface. Like if you want to write in a sheet of paper, the paper should be supported in the back end in some horizontal flat surface. Then only you can write smoothly, right? The same phenomena here. You need a particular thing to support the layer of the film what you apply, and hence you need the substrate. So it could be either the silicon, the glass, or the quartz, right? And the thin film deposition. So to deposit the thin films on the substrate, we need some materials. So usually we go on with either polysilicon, silicon dioxide, silicon nitrate, or few polymers. So the fundamental concepts in MEMS, what happens is we need to develop an thin film, and to develop the thin film we need some support, so that has to be a substrate, and these are the materials what we use in. Okay, so and apart from that, the substrate plays a vital role related to its physical phenomena. Apart from that, the chemical aspect also comes into picture. So you have a substrate and you apply a layer of thin film. So how it gets fixed on the substrate? You should be having some chemical reaction to go on, right? So for that, we need to use some techniques. It could be either CVD we call in short form, and it is commonly known also. It is nothing but chemical vapor deposition. So this is the most commonly used phenomena to apply a thin film on a substrate so that it gets solidified and you get the required film on the substrate. The other method is called as atomic layer deposition. Okay, so these are the two common methods which are being used to develop a thin film. Please use the appropriate word. Right, when it comes to the chemical aspect, you are using CVD to develop a thin film on the given substrate. If you won't use a chemical method, the film will be somewhere and the substrate will be somewhere. You won't get development of the film as per the required pattern, and hence chemical technique is very much essential to develop the required thin film on the given mask. So in brief, if you want to understand, this theory of MEMS mainly tells you about the thin film deposition. So this thin film deposition could be either done by means of physical deposition or by the chemical deposition. In physical deposition, we have two methods. One is the evaporation technique, which is called as PVD, and the other one is the sputtering. Means you use a sputtering unit or a spray gun and you sputter the film uniformly on the layer of the substrate. So a thin film will get deposited on it. So there is no need of any chemical funda to come in between, and hence the name physical deposition. If you go for chemical deposition, then we have two types, what I told you already, which is chemical vapor deposition and automatic layer deposition. So these are the techniques which are followed to develop a thin film on the given substrate. Any doubts related to the basic concepts? Is it clear enough?
Yes, ma'am.
Okay, so when that is done, once the layer has been applied, you should be able to develop the given pattern, because you have seen many MEMS device like a microchip in which the micro design will be done and accordingly the pattern will be developed and the unnecessary part will be etched out. So this is nothing but developing a film and using a mask to get the required design on it. It is nothing but the pattern. So then you will immerse that in either CVD or the other process. So that chemical reaction will etch out the unwanted material and it only retains the required pattern on the chip. So that is called nothing but as etching. So the first step is applying a layer of oil film on the substrate, which is nothing but development of a thin film. It could be either done by physical deposition or by chemical deposition. Means to say that you have a support, which is nothing but the substrate. So on the substrate, you have a layer what you have developed, the thin film, either by physical deposition or by chemical. So once the film has been developed, you should provide the patterns into it, which is the type of design you want on that thin film. So you need to transfer a pattern into the material after you deposit, right? So this will be achieved when you keep the specimen ready for etching out. Means when you remove the excess part, then the pattern will be retained. It is nothing but like the sculpture who will use a stone and he will start hitting from one end to the other until the required pattern is developed on the stone. Similarly, first you will provide a base substrate, on that you will provide a thin film. So later you use a technique called lithography or photolithography. So this is the technique used in order to get the required pattern on the thin film. So the excess amount of the material will be etched out. This part is called to be as etching. And this removal of the etching could be done either by wet etching method or by dry etching method. So these are the two methods what we have in order to remove the excess material. So as the name itself suggests, what happens in case of wet etching? So the substrate, along you have a substrate and a thin layer of the film what you have developed, and you have made a pattern on it. So this entire substrate will be dipped into a chemical solution, right? So this chemical solution will remove the waste material, yeah, unwanted material, right? And it will retain only the target material which has been needed. So and hence you will remove the excess material, which is nothing but called as etching. Okay, so this is one way. The other way is dry etching. So what you do in this, here a material is putted on the substrate or it is dissolved from the substrate. By what means? It is either by plasma or gas variations. You will be having a plasma or a gas variations in a cylinder kind of thing. So you will just putter this material of plasma or the gas variable on the substrate. So it will remove the excess amount of material which is not needed, and it will only retain the part which has been required. That is the pattern what you are retaining. So these are the two methods what they usually follow. I'll just show you a diagram, you will understand. Okay, so this will be an substrate. Here it is made up of silicon substrate. So above that you will be using an silicon oxide layer. You have to be very careful. And above that the thin film has been deposited. So you might have a question now, why the silicon oxide is used in between the substrate and the thin film? Because between the thin film and the substrate, you should be having a proper bonding. To have a proper bonding, you should be having an adhesive layer. So adhesive layer is deposited between the thin film and the substrate so that you get a proper adhesion between the two. And then you will apply the pattern. So this is a pattern what is being needed. So you apply a pattern, means you deposit the pattern as I told you before. Right? So in patterning, so you will deposit the pattern which has been needed. So after you deposit the pattern, you will just put a mask on it so that it is safeguarded. So once this device with n number of layers is ready, so then you will subject this for etching. So it could be either due to chemical, either due to wet etching or dry etching. So when you subject this to etching, the excess material is removed. So now you can see you have excess amount of material here. When you subject to wet etching or dry etching, the excess amount of material will be removed. Only the required pattern is formed over here. So this is by the wet etching concept. Okay, the same thing I'm telling over here. So these are the procedures which are being followed. So what are the first step? First, you will develop a film. To develop a film, you need a substrate, right? And this film could be deposited in two methods. One is a physical deposition and the other one is a chemical deposition. In each deposition, you have two techniques, what I have told you. So once this is done, you will try to deposit the pattern on the given thin film what you have developed. So excess amount of material will be removed out either by wet etching or dry etching. And one thing you have to remember, what is the technique used for achieving the pattern? It is either by lithography or photolithography. These are the two common techniques which we use to develop a pattern on the given thin film. So we'll go in depth related to photolithography after some time. So these are the basic steps one has to follow. Any doubts related to this? Any doubts?
No, ma'am.
No, ma'am.
So this is about the fabrication process steps. So now we have to go for the concept which is called as photolithography. So this technique is used to make what? Can anyone let me know? I told you right now, photolithography is used to make it what on the pattern, right? Photolithography is used to develop a pattern on the thin film what you have developed. So this is the photolithographic technique what we usually use to transfer the copy of the master pattern into the thin film where you need it. Basically, we use the same phenomena to create the IC chip. So in IC chip, you need a circuit layout. So how you cannot directly draw a circuit layout on the thin film? You need some pattern and that has to be applied on the thin film by some technique. So this is nothing but photolithography, so which will apply the pattern of a circuit layout on the thin film so that circuit layout could be developed. Okay, so this is a technique what we use usually to develop a pattern on a thin film. And the substrate here is covered with a thin film of some material. I told you, which is nothing but silicon oxide. I told you what is the use of silicon oxide also. It will help to provide a grip between the substrate and the thin film. And hence, it is always essential to use an adhesive layer. Again, this adhesive layer depends upon the substrate what you are using. If you are using a glass, then you have to think about a different adhesive layer. Since we are using your silicon, the additive layer what we are using is silicon oxide. Okay. So we usually use silicon oxide in case of silicon substrate so that it provides a proper holding for the pattern which has to be developed. Okay, so this you have to keep in mind. So after this, a thin layer of organic polymer is being applied on the device. So first you have a silicon substrate, on that silicon oxide. So above silicon oxide you are applying a thin layer of organic polymer. So this is our thin film what we are applying on the substrate. So it will be the thin film deposition. And this thin film of organic polymer what we apply will be very sensitive to ultraviolet radiations. So you should be very careful. So it will be very sensitive to ultraviolet radiation and hence, okay, so this phenomena is called as photoresist. So once you develop a thin layer of organic polymer, it is sensitive to ultraviolet radiation and hence this organic polymer which is an oxide will be easily deposited. Since it is helpful in getting an oxide layer deposition, this phenomena is called as a photoresist. Why it is photoresist? Because it is sensitive to any kind of ultraviolet radiations and hence the phenomena is called as photoresist. So once this is done, a photo mask will be used. A photo mask, what does this photo mask contain? It is like a covering sheet which will be transparent enough. We usually can consider that to be as a glass plate. Once a thin film has been developed and solidified by photoresist, that layer has to be safeguarded. And to safeguard that, we use a photo mask. right? And this photomask basically consists of a glass plate. When you tell a glass plate, it is transparent enough. Okay, so this glass plate will be having an chromium pattern in it. Usually the mask will be coming with some pattern. So this will be having a pattern called chromium, means to say this will be having in opaque in nature. So glass plate is transparent. So above that glass plate, it will be having a chromium pattern. So it makes it opaque, means it will not be transparent and clear enough when you view from the top. So this coating has been applied, right? And it is placed in the photoresisted coat surface. So what do you mean by this? You will exactly come to know when you develop this thin films. Only by listening, it will not be so much clear to you all. But still, I will show some of the images later. Okay, so first you will develop first you will make a substrate. Above that, you will apply an silicon oxide. Above silicon oxide, you will develop a thin layer of organic polymer. Okay, so above this organic, this is not only organic polymer. After organic polymer, we have applied many things, and as the thickness is more over here, you will apply an organic polymer. Above that organic polymer, you should apply a mask. The mask will be transparent enough, and above that, you will be having a chromium pattern. So when you apply a chromium pattern, it will be not transparent. It becomes a little bit opaque in nature. So that you have to understand. Once this is ready, you will keep this across a photoresisted coated surface. So you have to keep in contact where the photoresist comes into picture. Later, when these layers are ready, you will expose this to ultraviolet radiations. So on the top, you will subject it to ultraviolet radiations. So due to this ultraviolet radiation, it transfers the pattern onto the mask to the photoresist. Because here you'll be having the pattern which has been applied, right? So when you apply ultraviolet radiation, this pattern will be deposited on the thin film which has been developed. And this is by the photoresist phenomena. Okay, so it could be either due to positive photoresist or it will be due to negative photoresist. If it is of positive photoresist, the required pattern will be retained here. If it is negative photoresist, the required pattern is etched out and the remaining part of the material is retained. You might need both the type of the patterns. If you want to put this above over here, so you should be subtracting some element from here so that it gets fit into it. It is like just components what you combine together to make a fit assembly. Similarly, if you want to retain the required pattern, you should go for positive photoresist. If you want to remove the required pattern, then you have to go for negative photoresist. So these are the two changes what we get depending upon the type of photoresist what we are using. And always one thing you remember, the positive photoresist is strengthened by the UV radiation. So when you apply UV radiations, this photoresist will be strengthened. Whereas when you apply a UV radiation to negative photoresist, it gets weakened. So these are the two differences what you have to know. So this is just about the photolithography. So photolithography we used only to develop the pattern. Okay, so the two concept is lithography and photolithography. In that I have explained you the photolithography concept, wherein you will be having a substrate. Above that you use an adhesive layer, silicon oxide. After that you will apply a thin film, right? So when you apply a thin film, then you will apply the mask. The mask will be transparent. So above that you have the chromium coating which makes it opaque. And after that you will subject it to ultraviolet radiation. If it is positive photoresist, it helps in retaining the required pattern here. If it is negative photoresist, it helps in removal of the pattern which wasn't needed. So this is how getting the required pattern on the substrate. You cannot just deposit a layer only to the required dimension in any circumstance. You have to apply for the entire substrate. Then only you can remove the unrequired material with the help of photolithography, which helps in depositing the required pattern. So this was only our device, the substrate and the adhesive layer. So now due to photolithography, we have developed a pattern on the device, right? So this is just to show the difference between positive and the negative photoresist. So this is about the photolithography technique. Any doubts in this? Hello?
Uh,
If it is clear, then okay. So I am going to move about the substrates. So I was telling substrate. It is nothing but a supporting layer. So what do you mean by it? You should be also knowing something about the substrate. You cannot blindly select any substrate. So substrate is the bottom layer which supports the thin film what you develop. So the thin film could be of a single layer or it can be multi-layered wherein you can make a stack of it and make a device, right? So, and it could be a unimorph or a biomorph layer. But in order to hold these thin films, you should be having a good supporting unit at the bottom. So this is nothing but our substrates. So here you have to see the most common substrate material which are used in today's industries is nothing but silicon. Other than this, we have quartz as well as glass and sometimes steel also. But the most common thing is silicon because it is flexible and it is economical, right? So it is better to use for a longer run. So in many microelectronics industries, it has been used successfully and it is still serving as a good substrate material. And I hope it will continue in future also as the best due to many reasons. And remember one thing, when we go for miniaturization, I have told you scaling of the given device with respect to various factors like scaling of geometry and other parameters what we have dealt, right? Why this silicon is suited to be as a good substrate, so that you should understand. It has some key factors. One thing is silicon is available in abundant. It cannot be exhaustible, right? It is available in abundant. And second most important factor is it is inexpensive. It is cheaply available, right? And the other thing is it can be processed to unparalleled purity. So what do you mean by it? So it can be processed easily and it will not be contaminated, right? It will hold its purity to 100% irrespective of the processing method which has been followed. So these three are the very most important factor to select any material. It has to be abundant, it has to be inexpensive, and it could be easily synthesized or processed with less amount of purity, with more amount of purity and less amount of contamination. So this is the major plus point of silicon, why we are using as a substrate. And secondly, what is its functionality? Because the silicon will provide you an ability to deposit the thin films in an easy way. Sometimes the material should support, right? So if you apply a layer of thin film and you're not having a proper adhesiveness or a proper contact between the two layers, if it is dismantling easily, then you cannot claim that silicon is a best substrate. It should be having a good compactness with the other layers what you deposit, right? And hence this is the most important factor why we are using the silicon, because it could be easily help in getting the materials to be deposited, and it also provides a proper bonding to it. So this is the second important factor. Sometimes the silicon and the other layers are deposited without having an adhesive layer also in between, because it has a little bit of good adhesion between the layers. If you need to develop multi-layers, more than 2, 3, so then it is essential to use silicon oxide as an adhesive layer, as I showed you in the previous image. Silicon oxide in between the substrate and the thin film. Okay, so if for single or 2 layers without the adhesive also could be done. And next thing is reproduction of silicon device shapes using photolithography are perfect for high levels of MEMS precision. Means to say it provides a good precision for developing of the required shapes by the concept of photolithography technique. So it provides a high definition and high precise shape which has been needed by using the photolithography technique. And this is the next point why we go for silicon as a substrate. And lastly, one more thing. A silicon wafer, what we develop, it usually consists of hundreds of identical chips. Okay, so it is not like a single chip. The silicon substrate or the wafer, what we use, will be a combination of hundreds of identical chips. So these are the plus points of why we use substrate, why we use silicon as an substrate material. But when you select a material for the substrate as silicon, you should think about its crystalline structure. So you have to go back to your basic physics and see the lattice crystal structure across which plane the silicon orientation will provide the required good results. So you can see that the feasible lattice structures for the silicon are across 100 plane, 110 plane, and 111 plane. So this you have studied in your basic physics. So when you go for an orthorhombic crystal structure of a silicon, right, you can check the orientations here across the given plane. So as per the lattice, this is a crystal structure of 100 plane. So this is how the silicon crystal looks at 100 plane. If you are going for lattice structure of 110 crystal, so then there will be orientation of these ions of the silicon as indicated. And this is for 111 plane. So in these three crystal structures, we will get a good possible requirement as a substrate for MEMS device so that it can provide the good compactness between the layers of the thin film what we need to deposit. So these are the low crystallographic index planes which are suitable for MEMS devices. This is about the substrate. So any doubts related to the substrates? Is photolithography and the substrate part clear enough?
Yes, ma'am.
Okay, any doubts, kindly let me know in between at any time.
Yes, ma'am.
Yeah, so now you know about the substrate, about the thin film, what we have to deposit by using photolithography technique. I was telling you something like an adhesive layer. So it also consists of some of the adhesive material. So what are those adhesive material? If you go back to the diagram here, I told you this is the substrate made up of silicon. So now you have dealt about the silicon substrate. And I told the pattern will be deposited by means of photolithography. That also you know. So now in between, I told you that there will be an adhesive layer which provides a good bonding between the film deposited and the substrate. So we should know about this between layer, right? So what is that? It is nothing but the additive films which are being developed by using some materials, right? So which are the feasible materials as an additive layer? So that you have to think about. So the type and the varieties of additive films and the additive materials which are available for MEMS devices have a huge possible combination than that of its substrates, right? Suppose if you are using silicon as a substrate, so which are the additive materials you can go for? It is like single crystal silicon, polycrystalline and amorphous. Okay, so for that, the feasible substrates are like silicon compounds. So silicon compounds, you have again varieties here. So these are the available adhesive materials. So in that, the most commonly used is silicon oxide, SiO2. So this is silicon carbide, right? So most commonly used is SiO2. So these are the additive layers or the additive films which are being developed for the silicon substrate. Suppose instead of silicon substrate, you are going for metal and metallic substrates, right? For those, what are the adhesive materials we use? So these elements are the adhesive materials which are being used. Okay, so you should be very careful about which is the substrate you are using. For that, which are the adhesive material you have to go in. Suppose for ceramics, if you deposit ceramics as a thin film, so you should be having a suitable additive layer for it. So always you should try to go to have an additive film or the material which is more suitable for ceramic compounds. So you have to check which are the compounds more feasible for ceramic layer of deposition. Accordingly, you have to select the additive films. Suppose if you're depositing organics on the substrate, so an adhesive layer usually which has been used for any type of organic deposition is either diamond, polymers, enzymes, or any other antibodies or DNAs for biological application. So you have different varieties of additive films based on the layer what you are depositing. If you're depositing the layer of silicon compounds, then these are the additive materials. If you are depositing metal and metal compounds on the substrate, these are the additive materials what you have to use. And if you are depositing a ceramic layer on the substrate, you should be always checking the compactness related to the ceramic compounds and how feasible it is to have a bonding, because ceramics will be very brittle in nature, so you should be very careful in selecting an additive layer for it. Okay, so for others you can go on without the additive film also if the thickness is very less, but for ceramics you should be very careful. And also for organics, the additive layer should be still strong enough. So these are the different variants of additive layers which are available to act as a good adhesive layer between the silicon substrate and the thin film what you have deposited. Any doubts related to the substrates and the additive films?
No, ma'am.
Okay, so if that is clear, so now you should come to know about the other fabrication methods. I have explained you in general how a pattern could be deposited, the concepts of the substrate and the thin film, how you deposit, and the adhesive layer. So now, fabrication methods, you have different techniques. I told you that to fabricate, we go with wet etching and dry etching, right? So this also you have to think about. So how do you proceed for this wet etching and dry etching? It comes into the category of bulk micro machining. Bulk micro machining is not a new word. It has been used from many decades before. So wherein you were using this phenomena to develop the micro machining in bulk, right? So this is the oldest micro machining technology which has been available. So this technique usually involves selective removal of the substrate to produce the mechanical component. So it etch out the extra part of the substrate to produce a mechanical component, but the thickness of this component will be little bit higher, and hence the name bulk micro machining. Okay, so this technique also accomplishes either of the two methods, either the physical or the chemical process. The physical and the chemical process I told you in the beginning only, right? So if I go back, so you have a physical deposition and the chemical deposition. Under both, you have again two different techniques. The same thing has been told here, but in the concept of bulk, and hence the name bulk micro machining. So by using the process of chemical or physical, so you will etch out the required material. So the etching out could be either done by chemical wet etching, wherein you will be using a chemical solution to remove the excess amount of the material. Since the chemical solution is in wet condition, it is called as wet etching. The word etching refers for the removal of the excess material, and hence it is called chemical wet etching. And it is more popular. Why? Because it has a high etch rate, okay, and it is very selective in identifying which is the material to be removed. Usually when we do masking, right, we will provide a color coding. So at that you will be indicating which is the part which has to be removed and which is the part which has to be retained. So based on the color code, it will just etch out the unrequired part, and hence it is called to be as a chemical wet etching. Apart from that, it has two more type of wet etching. So under wet etching, I told you what do you mean by wet etching in the beginning. But under wet etching, we have three categories. One is the chemical wet etching, where we'll be using the chemical solution to etch out the unwanted material. The next is isotropic wet etching. So here, the etch rate is not independent on the crystallographic orientation. I told you about the crystallographic orientation also. Right? So here the wet etching is not related to the crystallographic orientation in case of isotropic etchants. Just a second. yeah, in case of isotropic wet etching, it will not be dependent on the crystallographic orientation of the substrate. I told you that the substrate crystallography plays a vital role. So it will be good enough in 100, 110 and 111 plane. But if you go for wet etching, okay, so it will not be having any factors associated with respect to the crystallographic orientation of the substrate. So that is for isotropic wet etching. So it mainly depends upon the categories of the material what you are using. Is it isotropic material or is it anisotropic material? But if you are selecting an anisotropic material and if you are going for wet etching, so then the etching rate what you select will mainly depends upon the crystallographic orientation. So the etch rate will be different for different crystallographic substrate. Suppose if you are using a substrate of 100, then the etch rate will be different because it is an anisotropic material. If it is an anisotropic material, it varies with respect to its lattice structure. If it is an isotropic material, the properties will not vary with respect to lattice structure. So it is always feasible to go with isotropic material for any type of application and developing the device. Or else with respect to the lattice structure variation, the properties of the material keeps on varying. So you should not always go for an complexity. Always better to go for an isotropic material. But if you are going for anisotropic, you should be careful about the substrate lattice structure what you are using. So then the properties you should claim that the properties what you are getting is with respect to the substrate crystal structure of 111 plane. You should specify then which is the substrate crystal structure you are using. So you should be very keen about it. So this is nothing but the anisotropic wet etching. So these things you should be very clear enough. Okay. So here in the image, it shows you an isotropic etching. This is of A, right? And this is A, and this is without agitation. And this is with respect to the different planes. So this is for 100 plane and this is for 110 plane. So by this you can see how the variation in the etch out. So the unwanted material are being removed here. So regular isotropic etching, okay, it shows you how the pattern is removed. So if you are going with agitation, so then the amount of the removed pattern is different. And suppose if you are going for anisotropic wet etching for a substrate of plane 100, so this is how the pattern looks like. And suppose if you go for etching out for an anisotropic material with the substrate for 110 plane, so this is the way how the pattern looks like. So by seeing the pattern, you can claim that which is the type of wet etching is been done. Is it regular etching? Yeah. Is it with respect to agitation? Yeah. Is it with respect to anisotropic wet etching of different planes? So this is the thing what you have to understand. So I have just given this for your more reference in depth. So which was supposed to be given to you all, the information I've already given. So next is anisotropic etchant. So in anisotropic etchant, what happens is we use an common anisotropic etchant material, which is called as potassium hydroxide. So this is an anisotropic material, what we are using for removal of the excess material. So here the structures which are being developed on the substrate mainly depends upon the crystal orientation of the wafer or the substrate, as I told you. So it could be 111 plane, 100 plane. So based on that, the etchant layer will be developed. So it is shown in figure 19C and 19D. So this is 19C. This is C and this is D. Okay, so these are the different patterns what we get. The same thing has been shown over here. So I don't want to waste much of the time. So next we want to come for dry etching. So dry etching, I told that it will be done without the inclination of any liquid media here. You will be having an plasma based technique. So it is nothing but a wafer phase or a plasma based method. So with respect to the vapor pressure, the unwanted materials are etched out. So here we'll be using some reactive gases or vapors. So reactive gases or vapors will not be very active if it is at room temperature. You have to subject that for some external high temperature, and hence here the gases will be made to pass on through the pattern at high temperature. So this will remove the unrequired pattern. So the most common type of plasma based method which has been used in MEMS devices are RIE. What do you mean by RIE? It is commonly called as reactive ion etching. So when you pass a high gas, when you pass a reactive gas or a vapor at very high temperature on the substrate, so what happens is it gets reacted with respect to the ions which are there on the surface of the oil, thin film which has been developed. So it removes the excess amount of the material, and other retained material will act as our pattern. Okay, so this is the way how the material will be etched out in case of dry etching. So here the ions will be accelerated towards the material, okay, by means of a plasma phase. And when it is subjected to a high temperature, nearly in between 150 to 250, okay, the etching out takes place. For some of the material, you might need still more high temperature. It depends upon the melting point of the material, what you are selecting for your deposition. So if the material what you have selected as a high melting point of more than 1000 degrees Celsius, so then you have to energize the ions by subjecting a high temperature vapor or gas above 1000 degrees Celsius. So these are the ways how the material will be removed in case of dry etching. So what is a common funda? In dry etching, you will be using plasma based method. So in plasma based method, what you will be doing, you will be having a set of reactive gases or vapors. So that will be passed at a very high temperature. So under plasma based method, which is the most important technique which has been used, it is reactive ion etching, which is called as RIE. So it uses RF power. So this RF power is very much in need to send the required chemical reaction across the ions. So how this ions will be energized? It will be energized by supplying this reactive gases at a temperature in between 150 to 250 degrees Celsius. And this is feasible if the melting temperature of the material what you're using is below 250. If it is above, then you need to go for 1000 degrees Celsius. So these things you have to be very careful. And one more thing, if you go for this RIE, you have to see that it is not limited to any crystal planes. So this RIE can go with any substrates what you have for different crystal orientations. The crystal orientations I told you already, so it could be across 100, 110 and 111 plane. So this is about the concepts what you have to understand in case of dry etching. Any doubts related to this?
No, ma'am.
Okay. So there is one more concept related to the deep reactive ion etching. So this are done in a very rare case and where an in-depth removal of the material is needed. And in short, it is called as DRIE. So this is called as deep reactive ion etching. In this, you will be seeing a much more high aspect ratios, means the etching ratio will be with respect to high aspect ratio, the ratio of the thickness of the material to the amount of the material etched out. So this is a ratio which figures out, right? So this is applicable and it is understandable as an alternative process wherein you are using for an high density plasma etching. So wherever the density of the material what you're using is high, we go for high density plasma etching, right? So in this case, you go for deep reactive ion etching. In short, if they call you or ask you as DRIE also, you should be able to know it is deep reactive ion etching, right? So in this case, we see that you will be having a protective polymer deposition across the surface to maintain the required aspect ratios. So this is the diagram here. So this is a normal etch and this is the deposition of the polymer and this is again the re-etch. So this is actual etching which takes place. So after actual etching, you will just make a layer of the polymer deposited. Why you apply this layer of the polymer? Because it acts as a protective polymer surface. So it protects this part and later you will again dig and re-etch. So you have etched so many material here. When you observe for the previous case in normal etching, you are not removing that much amount of material. But when you go for deep etching, right, you can see that this is a normal etching and to go for deep etching you usually apply a protective layer so that the other boundaries will not be affected and then you again re-etch. So this is like 3/4 of the given material has been etched out at a particular area to get the required pattern. So this is achieved by means of deep reactive ion etching. So this also you should be able to understand. So you are almost done with respect to different types of fabrication techniques, right? In general, and we have dealt with bulk micro machining. In bulk micro machining, which are the parameters which comes across the three type of etchants we have discussed, and then we have dealt specifically with respect to dry etching and also the wet etching. And apart from that, the surface what you have developed should be micro machined to have a smooth surface without any contamination, right? So for that, we call it as surface micro machining. So this process starts with the deposition of a thin film which acts as a temporary mechanical layer or sacrificial layer. So this protects the entire device. If something happens across the surface, it is a sacrificial layer. It can get damaged, but it protects or safeguards the layer which are being developed and packed safely. Okay, so this is usually called as a sacrificial layer. So surface micro machining is done in order to safeguard the layers which are needed. It is just an extra layer which will act as a sacrificial layer if any damage comes into picture. And below that you will be having the device layers which will be having the deposition, patterning and other layers. So what is the benefit of this surface micro machining? So that you have to see. So it is suitable for variety of structures. Any huge or small structure, it will protect and safeguard, and hence it is known to be as a sacrificial, and it can be used as an etchant combination also to removal of the extra material. Even this acts as the same thing. So any one of the etchant combination could be used for surface micro machining. So when it is being used, it could be used as a single-sided wafer processing also. Sometimes one side it can act as a wafer processing and on the other side it can act as a sacrificial layer. So it has two advantages on it. And what are the other plus pointers? It allows high integration density. See, you'll be having n number of layers. You use an adhesive layer also. All these layers should be stacked properly. It has to be integrated properly. It has to be added properly so that it plays as a single device and not as multi-layers. So this phenomena is there with surface micro machining. It helps in high integrity of the density of different layers in comparison to that of bulk micro machining. We have studied bulk micro machining, right? In comparison to that, the surface micro machining will provide a high integrity density. So these are the plus points of surface micro machining. But wherever you have a good advantage, you'll be having some drawbacks also. So you have to think about its disadvantages. What are its disadvantages? Is the surface micro machining materials what we use will be having the mechanical properties almost similar to the thin films. Okay, but What about the reproducibility of their mechanical properties is still unknown. Every material will be having mechanical properties, but what about its capacity to reproduce its mechanical properties when needed? So this is not still unknown. So this is only one drawback associated with surface micro machining. Okay, I can just show you a difference between the bulk machining and surface machining. Before me telling out, can you see this diagram and let me know what is the difference? I've explained you both bulk machining and surface machining. What you're understanding here by looking to the diagram? Can anyone see and let me know? It is clearly understandable. You should be able to tell me the difference if you have understood the concept. Be quick. I'll be calling the attendance. You people have to answer. This is a part of a quiz right now. I'll call one by one. You people tell me the differences. I hope I'll start up with Mohan Ambal.
Yes, ma'am.
Attendance plus question. Answer the question, you'll get the attendance. What is the difference between bulk micro machining and surface? As I've shown you in the diagram. What is the difference you're able to observe? Bulk micro machining, you have two types here, isotropic etching and anisotropic. I've explained you both. And similarly, in surface micro machining also, required pattern, everything has been developed. What is the difference you're finding here? What's happening to the substrate here? Kindly observe properly. Danush?
Yes, ma'am.
Yeah, what is the difference you're observing over here?
Ma'am, in case of bulk machining, too much of material removal is there, ma'am. Like it is wherein the selective removal of the substrate to produce related mechanical components, ma'am.
See, bulk micro machining was used in many years ago, wherein the excess amount of material was removed in two categories, isotropic and anisotropic etching. Okay, so I've explained you both. So in that, the substrate part was being etched out, if you observe here, right? So wherein in case of surface micro machining, the etching, the pattern making, everything will play a vital role across the surface. The no amount of material will be digged or removed from the substrate. You can observe, right? The entire substrate is available here. So after applying the layer and removing it also, the substrate is not affected in any way. And later you have added one more structural layer, but still the substrate is safeguarded. And then the required layer is retained and the sacrificial layer is removed out, but still the substrate is retained without etching any material from it. So by this, you see that the surface, the structure will remain strong because the substrate, the foundation of it is as usual without any etching out the material. Whereas in case of bulk micro machining, to get the required pattern, the substrate is etched out in both the cases for isotropic and anisotropic. Can you tell me the difference between isotropic and anisotropic? I spoke you with respect to the substrate crystal structure, so which claims to be isotropic and anisotropic. What did I tell you? If the material used is isotropic, then the properties will not get affected if you're using any crystallographic index of any silicon substrate, right? If the material used is not isotropic, then the properties will vary with respect to the crystal structure of the substrate what you are using. So based on that, the pattern of the etch out will be different in both the cases, isotropic as well as anisotropic. So this is the old method which has been used. But whereas now in surface micromachining, all the process could be achieved without removal of the extra material from the substrate. So this is the difference between the bulk micromachining and the surface micromachining. Hope you can understand now.
Yes, ma'am.
See the next figure here, what I'm showing. Always in surface micromachining, we use a sacrificial layer so that if anything etching out has to be done, it will be done in this layer so that the substrate will not be affected. But whereas in case of actual bulk micromachining thing, what we used to do is we used to have a surface, we used to have a substrate, and this etching was being done in the substrate. We didn't had any supportive layer which acted as a sacrificial for removal. The substrate itself was a sacrificial layer where we used to do the etch out. But now the things have been changed. We will use an sacrificial layer. So this sacrificial layer will help in removing or etching out the unwanted material. So this substrate will be safeguarded. We won't remove any excess material from the substrate, which was done in case of bulk micromachining. This is the difference. Hope is it clear?
Yes, ma'am.
Yeah, so you have to observe and understand. No? If you won't tell me properly, then what is the use of explaining you guys? So here you can see this is the substrate. So above the substrate, instead of adding adhesive layer, a sacrificial layer will be applied. So once the sacrificial layer will be applied, on that you will place the pattern which has to be retained by means of photoresist. So this could be positive photoresist or negative photoresist. So later you will etch out. So this is the first etching. So when you etch out, this pattern will be retained and the sacrificial layer will be removed at this end as well as this end. So you can see in the third diagram, the sacrificial layer is retained only across the pattern which was there before, right? So the remaining amount of the sacrificial layer is removed, and hence the name sacrificial layer. So on that, a layer of material will be deposited. So this deposition again takes place by the photoresist phenomenon. So once this is done, you will go for the second etching out. So once the second etching is done, you have two layers of the pattern now, 1 and 2. So remaining part of the sacrificial layer is removed. So this is how it will operate. Okay. Any doubts now?
No, ma'am.
So kindly understand the phenomena, then only you'll be able to explain it. Okay. So everyone please write your name and USN in the chat room. Danush,
Yes, ma'am.
Mithun,
Yes, ma'am.
Mohan Ambal,
Yes, ma'am.
Sandesh,
Yes, ma'am.
Srinidhi, Sukrut,
Yes, ma'am.
and Sri Harsha.
Yes, ma'am.
Yeah, please go through it, understand the concept. By looking into the diagram, you should be able to figure out which type of etching it is. Is it bulk micro machining? Is it surface machining? How it has been etched out? What is the process? So by looking the diagrams, you should be able to explain. That shows that your concepts are clear enough. Until then, it will be like a big mess. So kindly go through it. Okay, so in the next class, we will go with respect to micro integration and other parameters. So until there, take care and have a nice day.
Thank you, ma'am.
Yeah, thank you. Bye bye.
Thank you, ma'am.